Okay, so today's speaker is Dr. Kevin Folliard. Kevin has been at UT for almost 18 years. He did his PhD at UC Berkeley. He worked at the University of Delaware for a few years. He worked in industry for a few years. He was an intercollegiate basketball player when he was an undergraduate. And Kevin is also the director of our Laboratory for Infrastructure Materials Engineering at the J.J. Pickle Research Campus, or some of you might remember as the Balcones Research Campus. Kevin is a great teacher. He's won a lot of teaching awards. I've seen him speak, and just I don't know anything about concrete, but when Kevin speaks, I feel like I do know something about concrete. And then when he's done speaking, I feel like I don't know anything about concrete again. But at least when he's speaking, I feel warm and fuzzy inside about concrete. He's going to speak to me today about our crumbling concrete infrastructure. Kevin. Nice photo, by the way.
Oh, thanks. So first of all, good morning. I'm really happy to be here today. Get to see a couple of my old students in the back there, a couple of other colleagues, so it's great to be here. I want to thank Rich for inviting me to speak today. And what I'm going to be talking about today is our reinforced concrete infrastructure, which is not in good shape, to put it nicely. If you look at, this is not the most recent, but the grades are essentially the same. If you look at our annual ranking that we get from American Society of Civil Engineers, we average a D+. We used to call that the gentleman's D+ when I was in school. That's when you just had enough to pass your chemistry class. But it doesn't really pass for our infrastructure because we're in pretty bad shape right now. A picture is really worth 1,000 words. There's a lot of different issues that affect our reinforced concrete infrastructure. My area of research is related to durability, so it's more kind of long-term progressive decay as opposed to, say, a load-induced failure. These are all examples of different types of deterioration. Most of that work I do is in the area of durability, and usually I'm looking at structures that are in not very good shape, but I like to always remind people that, in fact, most of the time we get it right with concrete. It's a very forgiving material. We do over-design it a little bit, and for the most part, it does extremely well in most of the environments in which we place it. That's the good news. And in Texas, that's certainly the case. We have structures here that go back over 100 years now, reinforced concrete bridges, still in very, very good shape. So we can do it right. We know we can, but still we end up having failures. What you see here on the left is alkali-silica reaction, which I'll talk about a little bit later. Probably the number one issue for us in Texas nowadays. Corrosion is the number one issue worldwide by far, which we also have here in Texas as well. So if you look at the situation here in Texas, you'll see we have problems. This is a high mass illumination pole in the Houston district that suffers from alkali-silica reaction, which is an internal form of expansive reaction that occurs. And there are countless numbers of these high mass poles, foundations in the Houston district, only of which a handful have been repaired to date. The big concern here is if you have a very big wind load on here, they're worried about the extensive cracking leading to a failure in the system here. So they have done some FRP repairs on some of these, but it's just the tip of the iceberg for the problems that we have here in our state. When I first got to Texas, I came out to the lab the first day, and one of our technicians had this sign on, which I kind of got a kick out of at the time. I'm originally from Massachusetts, and so I got a nice warm welcome when I got here. Texas is my home now, and I love it. And so come a long way since then. So one question that I'm often asked is, why is our infrastructure in such bad shape? There's a lot of reasons for this. Some of them are purely economical in terms of the issues. But one thing is that inherently we're really good at training our students to solve equations. Here's some wonderful structural equations, which I can't solve because I'm just a concrete guy. But our students are incredibly good at solving any equation that you put in front of them. They spit that stuff out. It's incredible. What they're not so good at, or not so interested in, is chemistry and the material side of concrete and in structures in general. Here's a professor with a bunch of chemistry on his mind. The student has just blanked out. He's thinking, wondering if he left his iron on at home as he gets this lecture. And unfortunately, this is the rule and not the exception most of the times with civil engineers. I picked civil engineering because I hated chemistry. I had no idea I would spend the rest of my life learning material science of concrete for the first time. It's inherent that the chemistry side of things just isn't appreciated as much, but it goes beyond that. If we think about us as instructors in universities, we have very little emphasis that we place on the material side of our infrastructure. If you think about a typical undergrad that comes through UT, have about 124 credit hours, of which roughly 1/3 of one credit hour, or 1/3 of one class, so that's about 1 credit hour, is devoted to the material side of our infrastructure. So less than 1%. And it's really hard to increase that percentage because we have so many other courses that our students have to take. So unfortunately, a lot of times our students come out underprepared for the infrastructure that they're going to be dealing with. So ideally, they would get this training when they get out of school, and one place you would look for that would be something like the ACI 318 building code, which is the most commonly used building code worldwide. But if you look at the materials and the durability aspects within the building code, again, less than 1% of the total coverage of the building code is devoted to the material side of concrete. So we have a bit of a deficit we have to work through. I'm very lucky to be at a place like UT where we have great students, and the university allows me to teach concrete, which is really the only thing I marginally know. And it's a wonderful thing to be able to turn the light bulb on with students and get them interested in materials. But it's a team effort. We all have to compensate for the fact that we don't have enough coverage in our curriculum, nor in professional engineering to kind of give us this knowledge. If you look at these concrete durability problems, there's so many different facets that we have to deal with. Many of these are chemical in nature, things like corrosion, alkali silica reaction, sulfate attack. Pretty much all of these forms of attack will make the concrete expand internally and ultimately crack the concrete in tension. We have some physical forms of attack here as well that also create some internal expansive stresses that can crack the concrete. Now, as Rich mentioned when he introduced me, I started off at University of Delaware. When the job opened up here at UT, I had no choice but to come because this is concrete jungle right here in Texas. More concrete infrastructure than any other state. And if you look at these durability issues, every one of them, with the possible exception of physical salt attack, has been observed here in the state of Texas somewhere. So a lot of opportunities. With challenges come opportunities. And with a huge state like Texas, 50,000 bridges, we have 85% of the nationwide reinforced concrete pavements. So it's a really great place to live and to teach because we get to see all of this right in front of us. Now, one thing that unites all of these problems with durability is every one of these requires water to find its way into concrete. Because the water is what's going to be bringing in the chlorides, bringing in the sulfates, bringing in the acids to attack the concrete. And anything that we can do to reduce the ingress of water will prevent many of these issues from occurring in the first place. So it's always kind of our first go-to when it comes to trying to produce durable infrastructure. Frank Lloyd Wright put it right, sorry for the pun there, but that architecture is a struggle against water. My PhD advisor at UC Berkeley was P.K. Mehta, and he told me for my first week when I was in grad school, he told me ions don't fly, they swim. So keep the water out and keep out all the aggressive entities. Now, unfortunately for us in concrete, we don't have the luxury to actually measure the rate of water movement through concrete. It's very challenging experimentally to do that. But some people have been able to do it in the lab, and we do have some other surrogate tests that give us comparable numbers. But if we just look at some of the data that's been generated on the permeability of concrete, this data here is showing permeability on the y-axis and water to cement ratio on the x-axis. And there's a lot of different data from different sources here, so it's not a perfectly straight line by any means. But what you'll see is if you lower the water to cement ratio, this is our standard litmus or benchmark that we use for concrete strength, but also for concrete durability. If we lower the water to cement ratio from 0.6 to 0.4, we'll increase the strength by about 50%. But we'll reduce the permeability by a factor of 10 or more. So the water to cement ratio, although it controls strength, it is the key to reducing the ingress of water by keeping that water to cement ratio down. It produces a less porous structure, and it is what we're trying to shoot for in an aggressive environment. Now, one of the problems with this is that, unfortunately, in the ready-mix industry, we have water tanks on our trucks. And those water tanks say do not drink, because it's non-potable water. What they should say is do not use. Because unfortunately at job sites, anytime a truck shows up and there's no inspector, you get the universal drink water signal, and they add water to taste to get the right slump. And there goes the durability, not to mention the strength. So we've been trying to put these kind of signs on ready-mix trucks with not much success. We decided to just build driveways this way. If the concrete shows up and they're pouring this driveway, they will not add more water to this truck because it will go right down the hill. So this is a real picture. I found it on the internet, so I know it's real. But really, the hallmark of us being able to produce durable concrete in aggressive environments is to go beyond the plain vanilla mix that we're all used to, water, sand, cement, and rocks, and to use things that we call supplementary cementing materials, things like fly ash, slag, silica fume. These are materials that fundamentally change the chemistry as well as the physical characteristics of the concrete. I would argue that any time you're in an aggressive environment, it would be a disservice to everyone involved to not include at least one of these alternative materials inside concrete. Because the benefits you get are not achievable with any other means that are commonly available to us. What are we trying to do? One thing we're trying to do is we're trying to make it so that the porosity within our concrete is reduced. But furthermore, we want that porosity to be so segmented and separate that it's impossible for water to travel through open channels. This is what we call percolation theory. And what we want is to take a situation like this where we have large channels that water can easily travel through, and through the incorporation of things like fly ash or slag, we can segment this pore structure and essentially choke off the connectivity between the pores. And as soon as you achieve this, your level of water tightness goes up by orders of magnitude. Using things like fly ash are one of the easiest ways to achieve this in a way that will pay direct dividends in field structures. The other problem with concrete, where these materials help as well, is for any of you that have ever worked with concrete or tested it, we know that it often fails when we load it around the coarse aggregate particles. This is a region that we call the transition zone. It tends to be have a higher water to cement ratio. It tends to have a lot of crystals that tend to align themselves in a preferred manner, which means that under load, the crack will travel right through the interface. If you put this concrete out in a marine environment, the vast majority of the water and salt will actually travel around the aggregate particles because it's the path of least resistance. In many ways, this is the Achilles heel of concrete, is this weak link between the rock and the surrounding paste. There's not much we can do with a straight cement mix to remedy this problem. If we go with just poured cement, you're going to have porosity, you're going to have open links in and around the aggregate particles. But what we can do is put in things like supplementary cementing materials. Here's an example where we've put in fly ash and slag in this kind of a simulation. And now you can see that the region around the rock looks identical to the region away from it, that we refer to as the bulk paste. So by segmenting the porosity so that water can't travel through easily, and taking care of this weak region, we can reduce the levels of water and salt ingress by orders of magnitude. And this is really the way that we've been able to have such a good infrastructure in our state compared to other states. Now, what I'm going to do for the rest of the time here is focus on just a couple of different aspects of durability. Joe Kelly put it well many years ago: find the cause and the remedy will suggest itself. It's actually a wonderful use of the Toronto Sun newspaper here on the right. So with every failure, there's always some kind of a market that will come out of it. So what I'm going to do is talk a little bit today about 3 different aspects of durability, all of which are relevant to Texas and elsewhere. And what I'm going to try to do is just alert you to some of the trends that we're dealing with and some of the research topics that we're working on at UT right now. So I'm going to start first with corrosion. Corrosion of reinforcing steel is by far the leading cause of deterioration worldwide. In fact, statistically, if you take all the other degradation mechanisms combined, they still won't add up to the level of deterioration and the cost associated with corrosion-induced damage. This is an example of actually a bridge that was built according to the requirements that would be consistent with the ACI 318 building code, which tells you in a corrosive environment, you just have to limit your water to cement ratio to 0.4 or 0.45. It doesn't tell you anything about using other chemicals, how to cure it, whether or not to put fly ash in there. And based on our experience in the last 15 to 18 years in Texas, if you design a straight cement mix, it will last roughly 10 to 15 years in a marine environment or anywhere where you have de-icing salts applied. So our conventional techniques and our building codes are not adequate. And that's where education comes in, to try to get our students up to speed so they can go above and beyond what is the minimum requirements of the building code. Now, steel and concrete is actually a wonderful marriage to begin with. And that's because when you take plain old rebar and put it inside concrete, you have to realize that concrete has a very, very high pH. Typically over 13.1 or 13.2. It can be as high as 13.9. Any of you that ever done any backyard concreting may have had your hands peeled from that high pH environment. You can get 3rd-degree chemical burns from working with fresh concrete. That's why we have our undergrads, when they take the lab class, they have to wear gloves to be safe. The reason it's harmful for humans is because the pH gets close to 14. But for steel, this is a wonderful thing, because in the presence of a high pH pore solution, steel will begin to corrode a tiny bit, and as it begins to corrode, it forms a passive protective layer that will then protect the steel for the remaining portion of its service life, provided that a couple of things don't go wrong, which I'll describe next. That passivates itself inside of concrete. We did pick aluminum as reinforcement because aluminum is the exact opposite. It will corrode at ambient pH outdoors. It will be durable in that environment. You put it in concrete in a high pH environment and it will rust almost immediately. So it's not by chance that we pick low carbon steel for use in concrete. The goal then is to trigger this self-protective mechanism and to try to make sure that that passive layer remains intact throughout the service life of that structure. Now there's 2 things that can get in the way of this. The most common is that salt can penetrate externally into the concrete and ultimately reach the steel in sufficient quantity to break down that passive layer and open it up for corrosive reactions to occur. It takes about 1.5 pounds of salt per yard to break down this passive layer. And once you do that, you have about 5 or 6 years left before you have to do substantial repairs. So our goal when we design a reinforced concrete structure is to try to model it so that the salt never makes it down to the rebar in that quantity during its intended service life. In the US, this has always been perceived to be the number one and the only concern regarding corrosion. But what we're starting to see more and more is this second form of corrosion, which does not require salt at all. It just needs CO2 from the environment. CO2 is in the air that we breathe at about 0.035%. It will penetrate into the concrete with time under certain kind of moderate humidity conditions. And as it works its way into the concrete, it lowers the pH in a drastic way. It'll lower the pH below 9 as that CO2 front works its way through concrete. As soon as you lower the pH beyond 9, below 9, you will depassivate the steel in the same way that we did with the salts. Now in the US, we seem to be in denial that this carbonation doesn't happen. In fact, when most people tell you that, they say it only happens in other countries, and they always mention Brazil as the model country that has carbonation and just corrosion. I spent a week there this summer. I didn't see any carbonation, just corrosion. But the point is that there's no doubt that, in fact, this CO2 intrusion can affect our concrete structures, and it does, and I'll give you a couple of examples here. So first of all, if we try to prevent chloride-induced corrosion, we have a lot of different options available to us. I'm not going to get into all of these here today, but suffice it to say, there's enough tools available to us to prevent corrosion. First thing, we could use a non-chloride de-icer. That would be an easy solution. There are non-chloride de-icers that are out there. They use them on airfield pavements, but they're too expensive for bridges. And you'll see almost none that are actually used in practice. All comes down to economics. If you avoid the chlorides, you would avoid the corrosion. We can use membrane or sealers, something like a hot mix overlay. I'm a concrete guy, and that's probably the best use of asphalt I can think of. We have a good friendly rivalry with our hot mix folks. We say it's a great barrier for concrete. So my steel colleagues tell me that concrete's a great fireproofing material for their steel. So it's all one man's treasure is another one's garbage. So we can use membranes or sealers, and regardless of what you're going to do, you always want to start with producing a low permeability concrete, like I started off with. Low water to cement ratio, well cured, with the presence of fly ash and slag as examples. We can use coatings on steel, things like epoxy coatings. They have issues. I don't have time to get into them here today, but the big issue with any time you coat something in a corrosive environment is that if that coating gets damaged during construction or thereafter, the corrosion activity will focus right where that holiday or breach occurred. And you can get very severe loss of cross-sectional area that we refer to as pitting corrosion with the green steel. We can use non-corrosive metals. You can put stainless steel in concrete. It will not corrode for your lifetime or your kid's lifetime. But again, it comes down to economics. You do not see stainless being used in concrete hardly at all. And then the last thing we can do is add chemicals which are not intended to slow the rate of chloride ingress, but rather they allow more chloride to accumulate at the surface of the steel without causing damage. So we call this raising the chloride threshold value. Something like calcium nitrate would allow you to accommodate up to 10 times more salt at the surface of the steel without breaking down that passive layer. So there's a lot of different techniques available to us out there, and really not a reason to produce concrete that won't last its intended life. But the thing about steel is a very stubborn material. If you think about a dust-to-dust situation, you start off with iron ore as your raw material, you run it through a blast furnace slag, you process it, you create a steel product, which then, in environments that promote corrosion, will go through a series of corrosion reactions, with the last one going right back to Fe2O3. In our lifetime, if you come back 10,000 years from now, all of the steel that's out there will convert back to its raw material. It's kind of amazing when you think about it. And you'll see the same thing with concrete. it is going to want to revert back to its native state, which I'll get to in just a minute. So this corrosion can be a big problem. Now, one thing that we've developed for use by TxDOT and others is a software program that was funded by TxDOT about 10, 12 years ago. And it's a program known as Concrete Works. It is a free software program available online for anyone that's interested. And my only point of mentioning it here is that we developed a service life model that's built into it that allows you to go through a parametric evaluation of all your available parameters. So you can look at the effects of cement type, fly ash type, water to cement ratio, clear cover, and you can model it, and then with the goal of ensuring that your structure is going to last more than a target of, say, 75 to 100 years, which has become the norm nowadays. 100 years is very common for a new bridge. So TxDOT and other highway agencies are using these tools, and there are projects that are let where the owner, the contractor, has to prove that the structure they're building will last more than 100 years. And these kinds of software programs allow you to do that in a very simple but quite effective way. So coming back to the carbonation side, I mentioned to you this is a bit of the boogeyman of concrete. People don't think carbonation really happens, but it does. And in fact, any concrete that's exposed outdoors to the environment will carbonate at the surface. And when it carbonates, it means it reacts with the CO2 in the environment. And the primary product it forms is limestone. If you think about cement, it starts off as limestone. We drive off the CO2 to create free lime, make cement, make concrete, give it 1,000 years, all the concrete in the world will turn back to limestone and be hanging out with its steel, which has reverted back to Fe2O3. So I hope we're not around then, because this inevitably will be the future of all of our infrastructure. The goal is to slow it down so that it doesn't occur during the design or service life. These things are stubborn. They want to go in that same reverse direction. So here's Portland cement. We heat the raw material up to high temperature because we need the free lime, calcium, to react chemically inside concrete. We drive off CO2 with that reaction. We also burn fossil fuel to get to these high temperatures, which can be 2,700 degrees Fahrenheit. This is about 60% of the CO2 emissions from a cement plant. The other 40% comes from the raw material, and together they account for 7 to 8% of the worldwide CO2 emissions. It's inevitable. You cannot produce cement without producing CO2. But as I said, CO2 wants to go back to where it came from. And if you put concrete outdoors for many, many years, all of the hydration products in concrete ultimately will revert back to calcium carbonate. And when they do so, the pH drops to 9, the passive layer goes away, and we'll get rampant corrosion at that point. Now, one reason that we're in a bit of denial about this is that our structures out there have not been out there long enough to see this occur on a daily basis. But it's happening right now with structures that are 70, 80 years old. And we're starting to see carbonation depths that are 2 or 3 inches in depth. And a couple of examples of that. Here's a reinforced beam that was taken out of service, tested in flexure, and as they expected, the results showed that corrosion had reduced the load carrying capacity. And in fact, if you trace it, you'll see that the outer portion, if you spray it with a phenolphthalein solution, which is a pH indicator, it remains clear, which means that that pH is dropped below 9. And what you'll see is right next to it, you'll see steel, which has reverted back to Fe2O3, has formed rust. If we just go about an inch on the other side of it, you'll see that the inner core of that beam is still passivated, still has a pH over 13, and you see no active corrosion products next to it. So our goal then is to make concrete where that carbonation front doesn't make it down to the steel in the intended service life? Well, we see more and more carbonation-induced corrosion. We're starting to see a lot of it in building construction. We're starting to see a lot of it in LEED buildings. Now, LEED is a wonderful initiative for green building, and it's a great sustainability initiative. But one side effect of that is when you're putting in 40% fly ash into a building in order to get your green points, that kind of concrete is much more susceptible to carbonation than straight cement mix. It's one of the only cases where you actually make things worse by putting in this otherwise great material that we call fly ash. To illustrate that, this is some data out of the UK, and I'll blow it up here to kind of show it to you. What this shows you is curing time on the y-axis, and on the x-axis is fly ash content. For those of you not familiar with I'm sure you're all familiar with the LEED program, but it's really increased the amount of fly ash usage in order to reach your gold or platinum LEED status. And many of those structures will be 30% or higher in terms of their fly ash content. And typically, we don't cure, wet cure, building construction hardly at all, if at all. So what you'd end up seeing here is depths of carbonation that can be an inch or two, and this is only after a couple of years of exposure, compared to, say, a straight cement mix that's well cured. So it's one of the only cases where this high fly ash content actually can hurt you. And TxDOT is very concerned about this as well, so we've been doing some work with them. We have an outdoor carbonation station where we allow concrete to carbonate. We measure the depth with time. And this is a staggering effect right here. This is a straight cement mix on the left. Only 3 days of curing. Its depth of carbonation is about a couple of millimeters, maybe a 1/16 of an inch. In the same time frame, this mix here has a very high fly ash content, 60%. And you can see that the depth of carbonation has already gone down 1 inch in 1 year. It's not going to be much longer for this carbonation front to make it down to the steel. So just wanted to kind of touch on this point because I think it's a ticking time bomb in our infrastructure that has not received the attention that it deserves. But I think it's only a matter of time where it's going to show itself up. And it's not just fly ash that does this. If you look at older structures, anything built 60, 70, 80 years ago in Texas, straight cement mixes back then, no fly ash, so the rate of carbonation was a lot slower. About a millimeter a year, plus or minus. Well, unfortunately, this is an example of the Lake Buchanan Dam. I'm working with LCRA on trying to preserve this dam now. After 80 years, the carbonation has made it down to 3 inches, which coincides with the location of the steel. We're losing large sections of steel, of concrete that are just spalling off of this dam. The same thing is true of the Darrell Royal football stadium, which personally I think it's why we lost the last couple of years. Because of the But I am happy to report that they have a $3 million contract where they are now repairing the carbonation just in time for next year's season. So I'm convinced the repaired carbonation-induced damage will get us at least 5 or 6 more wins this year. So, I just wanted to leave you with that point about carbonation, that it does happen not just in Brazil. It can be old concrete or it can be new concrete. The last couple of points I just want to walk us through here in the last 10 minutes or so are a couple of other durability issues that occur. This one here, alkali silica reaction. How many of you have heard of ASR? Quite a few, okay. Well, we have about 1,000 bridges in our state, roughly, that we expect that have alkali silica reaction today. It has historically been our biggest problem. And what happens here is that you have a reactive aggregate. In this case, it's pretty much any sand or gravel that comes out of any riverbed in Texas will be reactive. And you put it inside concrete, and remember, concrete has this wonderful high pH. That same high pH that passivated our steel, but unfortunately, it's this high pH that actually dissolves the aggregate inside concrete. If we didn't have a rigid matrix, the aggregate would just dissolve and go away. But because it's a rigid, fixed skeleton of a network, the silica can't just dissolve away, and instead it forms a silica gel in situ, and that silica gel is just like the bag of silica that you get when you buy a camera. It has a huge ability, propensity to absorb water many more times its own weight. It's exactly what happens inside concrete when you have a reactive silica that reacts in an high pH environment. Is ultimately it produces silica gel, which then takes on water and leads to expansion and cracking. So this has been a real big problem for us in Texas and throughout the country. We've now seen ASR in all 48 of the contiguous states. Haven't seen it in Hawaii, but we've been looking a lot there. Haven't looked at Alaska very much, but we're looking in Hawaii as we speak. So the irony here, of course, is it's that high pH. The high pH that passivates the steel is exactly what breaks down this the minerals and leads to alkali-silica reaction. Now, the way that we ultimately control this is by reducing the pH inside concrete. But we don't want to reduce it so far that we depassivate the steel. So on average, we shoot for about a pH of 13. You put fly ash into concrete, you put low alkali cement into concrete, you'll get the pH down to 13. The aggregate doesn't break down, but the steel remains passivated. So in fact, that's how we design reinforced concrete structures with reactive aggregates, is we're actually designing it for a fixed pH. We don't tell the contractor that because they don't want to hear about a pH. They just want to know what's the solution and what's in the specification. So it's our job to translate the knowledge in a tangible way that anyone can use it in the field. This is the LaGrange electrical plant in Fayette. Pretty good sized cracking there. Good use of a crack card. Usually you do it in the other axis. Good use for it. And this is a big problem. We can prevent this by getting rid of the reactive silica, by reducing the alkali or reducing the moisture. And as long as you take care of one of these, the problem goes away. Now the problem is that to know what the right answer is, you have to be patient and you have to base it on long-term data and not very quick accelerated lab tests. The best long-term answer is actually field performance. The next best are large blocks that we store outdoors. But people don't want to do that. They want the fastest result possible. If we had a scratch and sniff test, it would be adopted instantly by every highway department. In fact, we're working on that as we speak. But what they want to run, they want results in 2 weeks. And the way to do that is to take a mortar bar comprised of that aggregate and put it in Drano solution at 176 Fahrenheit. I used to just joke when I said we put it in Drano solution, but then we actually tested it versus Drano. So the dashed line is the actual standard ASTM test. The green line is testing it with liquid Drano. Same exact results. People are using this now as a standard reference material now. We are driving this chemical reaction by exposing it to an incredibly high temperature that it will never see in practice, and to a pH level that is unprecedented. And when we start looking at this quick test on the bottom axis versus our more accurate test, which takes 2 years on the y-axis, we want these two tests to give us the same result, ideally. If you have aggregates that are in this quadrant or this quadrant, it means it passed both tests or it failed both tests. And this occurs about half the time. The other half of the time, we get the wrong answer. And keep in mind, this is the #1 test used by every highway department. So what ends up happening is we end up in some situations with what we call bad actors. These are aggregates that look like they're reactive, but they're really not. So it would be the Alec Baldwin of the world. But to be honest with you, this one isn't so bad because if you were conservative, you would think you're reactive and you would take preventive measures. This has been well known for about 30 years. What we didn't realize, and this is a big issue in Texas, is there are aggregates that actually pass this quick and accelerated and aggressive test. So you would think intuitively, it's got to be good stuff if it passed that test. But in fact, a lot of these aggregates will fail in real concrete. And these are what we now refer to as the really bad actors. I came up with this classification scheme about 10 years ago, and now quarries in Texas actually refer to their aggregates as Billy or Alec Baldwin. So perhaps my greatest contribution to science. Maybe my only. Just going to go about 3 or 4 more minutes here, if it's okay. So the last point I want to touch upon, so again, I just tried to pick a couple of points here that might be of interest. This is a map of the United States showing coal-burning power plants. And the only point I want to make about this is that in the last 10 years, we've moved towards a different coal source in Texas and elsewhere to reduce the emissions out of power plants. And to do so, right now about 2/3 of the power plants in the US are getting their coal all the way from Wyoming, Powder River Basin. And when that happens, as soon as you change your fuel at your power plant to meet this emission standard, all of a sudden your fly ash changes drastically overnight. It will change in a way where the crystalline aspects of it change drastically. And you'll notice, I'm not going to get into all the details here, but you'll notice that we actually sequester the sulfates, or the SOX, that would otherwise go up the stacks. We make them precipitate out in the ash. The good news is it's not going up the stacks as emissions. The bad news is it's staying in our fly ash. And it also affects the glassy phases. At the end of the day, what ends up happening is that when we put in fly ash, usually, here's a control mix that expands and cracks. If we put in the fly ash that we usually produce in Texas, which is a class F, or low calcium ash, made with local coal, it will completely suppress expansion by just taking 20% of the cement out. But when you take this new fly ash that's now changing overnight from the new coal source, you put it in 20%, it gets worse, and the more you put in, the worse it gets. Now, this is what your samples look like after 1 month of testing, overnight from changing your fuel source. It's great if you have a master's student who wants to finish in a month and have their whole thesis done by testing Class C fly ash. But this is a major, major dilemma, because we've lost about half of our good fly ash in our state. By good, I mean Class F. And we're now forming this ash. And it's not just the test method. If we do it outside, there's nothing to look at either. It completely fails. So this is what's happening now in our country, is that our fly ash, which we've lived off of for 70 years, is being replaced by a fly ash that's not as good, and the available quantities are dropping off to a point where we don't have anything to take the place of this fly ash. So, in summary, durability problems are everywhere, and they're solvable. There's really no reason to produce concrete that doesn't last for the intended service life. But we really have to understand what's actually causing the damage, and ultimately, we want to benchmark all of our laboratory tests with long-term field data. And this is the part that I'm the most proud of in my 18 years in Texas, is that we've developed outdoor exposure sites now. If you've ever been to Austin, we have about 1,000 blocks at our Austin site. We have sulfate samples in Austin. We have a site in Van Horn, Texas. We have a marine site, which is just an excuse for my students to go to the beach. I learned that very early. I always go with them, though, because I have to make sure they're okay. And we have an outdoor site for carbonation. And it's this investment in the future and having long-term samples that I think is ultimately going to allow us to improve our infrastructure. And I'm lucky that I'm in a place at UT that lets me just expand throughout the Pickle Research Campus. I think it's easier to ask for forgiveness than to ask for permission, so we just keep sprawling. Rich hasn't given me a hard time yet, so I think we're okay. And with that, I'd like to say thank you very much for your attention, and I'll turn things back over to Rich.
Questions for Kevin? Do we have time for questions?
Yes, sir.
Do you need the moisture for the carbonation, or is it
So carbonation is a bit of a funny one. It likes to be somewhere between 50 and 70% humidity. So if your concrete's saturated, you get no carbonation. If it's dry, you get no carbonation. But it's the concrete that's exposed to wetting and drying, like the front face of a building or the back of a dam, where you have continuous wetting and drying. So it's a very niche area that it occurs in. which is apparently what Brazil is all about. They have that narrow relative humidity range.
Yeah.
At least that's what I've been told. Yes, sir.
What's the ACI doing about all of these things?
Well, I've been very active in ACI for many years and still am. The big issue is that there's things that we don't have solutions for right now. The shortage of fly ash is going to have a bigger impact on this state than any other state. We have absolutely nothing in line right now that will take the place of fly ash. So we're doing a lot of research and development to try to make this Class C ash better and to maybe mix it with other chemicals. But there's a lot of work that needs to be done. ACI is supportive of it. But to be honest with you, I have not heard one person that has the solution to the shortage of fly ash. Yes, sir.
When you go in to repair your older structures, like some of these viaduct bridges that we have, like in Dallas across the Trinity, I've seen them just basically patching or putting a special grout mix over the reinforcement. Is there usually a special mix design that y'all recommend when you go back to repair these structures?
Yeah, so what you want to do first of all is remove the contaminated concrete, whether it's chloride or CO2, and chip behind the rebar, and then you will want to put in a concrete that's free of chlorides and CO2. But you also want to make sure that you don't set up a galvanic cell, because if you patch an area and now it's totally pristine, you have an adjacent area that hasn't been repaired. It actually sets up a cathodic situation where you make the area next to the patch corrode twice as fast. And that's the big problem. No one's really looking at that when it comes to repair. The easiest way to handle that is to take a sacrificial anode. We call them hockey pucks. It has basically a chunk of zinc. You embed it in the area that you're repairing, and then that zinc puck will corrode instead of the adjacent rebar. That's what we're going to be doing at LCRA. But most people don't do that because it's really expensive. And unfortunately, if you don't do it, you can actually make everything else around you corrode much worse. It's batteries that set up in a corrosion cell are very stubborn. Yes, sir.
You mentioned heterogenite as being a contaminant. Where do you see that in the state as a problem?
Yeah, so ettringite is a crystal that can form when sulfates work their way into concrete. To be honest with you, we have almost no sulfate attack in Texas, the classical sulfate attack, because we have gypsum in our soil and it's very low solubility. So we usually don't see ettringite being formed from external sources. Where we do see it formed is if the concrete gets really hot in the first day, the ettringite decomposes and then forms later in its life. That's known as DEF. How many of you have heard of DEF? Quite a few, okay. That's a really bad problem that I didn't talk about today. That'll make the concrete expand 4%. Unprecedented levels of expansion will occur if ettringite forms in hardened concrete. We have bridges throughout the state that are feared to have this problem or will have the problem. Yeah.
They still use workability agents in concrete and build water?
Yeah, we still use a lot of chemical admixtures to reduce that water content so that we can get the water to cement below 0.4 or 0.45.
Does that prevent people from adding water on the site?
No, they'll still do that.
They still do that?
Yeah. What stops them from adding water at the site is an inspector, which unfortunately we have very few. So, yes, sir.
Does the air entrainment, does that affect the rate of carbonation?
No, it's really a negligible effect. Unless you had a super high air content where you had a lot of coalescing of air voids. But in a normal 5 or 6% air, it's almost negligible effect in terms of the rate of carbonation. What affects it the most is the water to cement ratio, the fly ash content, and the curing time. Yes?
When you're thinking about the durability of concrete, obviously when you increase fly ash, you take care of the permeability issues, but you said that it also increases susceptibility to carbonation over time. Is there kind of a sweet spot in there that you should try to be?
Yeah, so it's a really good question. So there's actually a couple levers that you can play with. So if you have a LEED building and you have to put 40% fly ash in there, so you can't change that, what you can do is cure more and or lower the water to cement ratio at the same time. Unfortunately, neither of those options are received very well by the building community because we don't wet cure buildings. And if you lower the water to cement ratio, you typically need another half a sack of cement. And economically, people will tell you what to do with it. So, but there are options for producing carbonation-resistant fly ash concrete. We're working on that with TxDOT, and TxDOT's much more open to that. And right now, if you do a bridge deck with fly ash, you have to cure for 10 days, wet cure. That remedies most of the carbonation problem. It's the cases where you ignore it and you just let it happen without curing the concrete, which is what we see a lot of these lead buildings. Good question. Yes, sir.
I just had one other comment. You know, after listening to this about concrete, I'm sure glad I got into an area of civil engineering like geotechnical where we didn't have things that changed so much.
Right. That's a good point, but the good thing is that when things change, it leads to research funding. So, and then if we solve the problems, the funding goes away. So we have to be pragmatic in our response to these issues. We want to solve it enough to preserve our infrastructure, but not so much to stop getting funding. I'm just kidding by that. Yes, sir.
In the North Texas area, we've, well, I guess in the last 10, 12 years, pretty well run out of natural occurring sand.
Yep.
And we're using the crushed limestone as our fine aggregate. That's it. And personally, I think I see concrete in our area failing, having symptoms of failure earlier. Does this manufactured sand, so to speak, have any adverse effect on our concrete?
Well, it can. First of all, it's a very harsh mix. If you're using manufactured sand as your fine instead of a river sand, the workability is not so good. And so a lot of times you'll have issues with consolidation, which makes the concrete kind of open from the beginning. The bigger issue, though, and the reason that we're more worried about manufactured sand is if it's a pavement or a bridge deck, manufactured sand will polish very easily, and you'll get terrible skid resistance, especially in a wet environment. So in any case where you have a deck or a pavement, we limit the amount of manufactured sand to 30%. And then you have to put in 70% river sand with it. That seems to remedy that problem. But there's going to be a massive availability of manufactured sand. People will just give it away right now because there's not enough of a market for it.
So I think that we need a PBS show called Captain Concrete, starring Kevin Folliard. So there seems to be a lot of interest, and thank Kevin once again for great presentation.
Thank you. My pleasure.